Alright, so in the last video we talked about solving a system of differential equations linear, and that was the case where we had like real distinct eigenvalues. For example, I'm just scrolling up to this last case we had, 7.5 number 11, and then we found that the eigenvalues were all nice and real and distinct, and then we formulated our eigenvectors from that. So we had an eigenvector there, an eigenvector there. Must have passed by the other one. There it is. And so once you have your three eigenvalues and three eigenvectors, right, then you can formulate the solution in a straightforward way. Good. So today what we're going to talk about is what happens when we have complex. So what if lambda is complex? Well, first off, we should note that since our characteristic equation is a polynomial of degree n with real coefficients usually, we don't have differential equations with complex coefficients, so we'll just stick with the real coefficients. Then p, or the polynomial, can be factored into a product of linear and irreducible quadratic factors. By linear here, I'm just talking about degree 1, and here we have degree 2. Okay, and so by that I mean, for example, the characteristic equation might be equal to something like lambda minus 1 times lambda squared plus 1, right? So this would be our linear factor, and this would be our irreducible quadratic. Okay, and because of the irreducible quadratic is going to have real coefficients, the complex lambdas must come in conjugate pairs. Always. Okay? So therefore, if lambda equals alpha plus beta I is one eigenvector or eigenvalue, then lambda bar that's not a vector, lambda bar, which is the conjugate, lambda alpha minus beta I, is also an eigenvalue, eval. Similarly, if v is an evec, then v bar, v vector bar okay, our notation's getting a little funky there. V is, that's our vector conjugate, is also an eigenvec. Alright? Okay, so what we don't want is complex solutions, because our solutions should all be real. And so from our differential equations class, from DEs, we know that if y of t equals like u of t plus I times v of t solves y prime equals a times y, then so does u of t by itself and v of t by itself. Okay, therefore what we do in order to get our solutions to this differential equation, so given y equals e to the alpha plus beta it, v is a solution, we we don't take the complex solution, we take the real part as one solution and the imaginary part as the second. So that might be confusing, so let's see how that's going to work. Example, suppose we have y prime is equal to, how about minus 2, 1, 1, minus 2. Oop, I need another minus in there somewhere. Minus there, maybe. Okay, times y. By the way, the pattern is going to be a, b minus b, a. The minus could go either place. Okay, so let's go ahead and compute our characteristic equation then. By the way, do you remember the trick with the trace and the determinant? The trace is minus 4. The determinant is 4 minus 1, which is 5. So in this case, we have lambda squared minus the trace plus the determinant. Good, and then I think we can complete the square on that guy. Minus 1. So that gives me a lambda plus 2 squared equals minus 1, so lambda equals minus 2 plus or minus I. So you'll, by the way, you'll notice right, minus 2 there, and then this was our plus or minus I coming from there. Good. Okay. So now we need to find an eigenvector. So we solve a minus lambda, right, times v1 plus bv2 equals 0. And then you could go through and write down the entire system, right, if you wanted to. cv1 plus d minus lambda v2 equals 0. But in our case, what do we have? I'm just going to use the top equation. That's going to be minus 2 minus 2 plus I times v1 plus v2 equals 0. Yeah, I'm going to leave the other one off. So what does that give us? Minus 2 and then minus and a minus is a plus 2 and a minus I, so the 2's cancel, and I'm left with minus I times v1 plus v2 equals 0. So my eigenvector, do you remember the shortcut we had for that back in the day? 1 and I would be our shortcut. You flip them around, negate one of them. Good. So now we have lambda equals minus 2 plus I paired with 1I. Good. And now we go down and we compute e to the lambda t times v. And then we're actually going to want the real part and the imaginary part of this. That's a t there. So in this case we have e to the minus 2 plus I t times 1I, and that's e to the minus 2t times cosine of t plus I sine of t times 1I. This probably isn't terribly exciting watching me do this, but I think it's probably important to review a little bit. I'll just leave the exponential out because it goes into every term now. And so now we'll have a minus the sine of t, right? That'll be coming from the I squared. And then we'll have a plus I cosine of t. And now I get my two expressions, my two fundamental solutions to the differential equation from this. My full solution will be c1 times the real part of this expression, which is e to the minus 2t times the real part, cosine of t minus the sine of t, that's that first column here, plus c2 times the imaginary part of this expression, this being the imaginary part here, sine of t, sine of t, cosine of t. Good. And so this is my solution to the system of differential equations. All right. And so I just wanted to, so this should hopefully be familiar to you from our class in differential equations. I'm going to talk about what happens when we extend that to more dimensions, and then yeah, we'll see where we are at that point. See you in the next video.